Today I'm going to be talking about this powerjack inverter. It's rated for 15,000 watts continuous and 60,000 watts peak surge. Now, I knew better when I ordered this to actually expect it to do this much. But you know, they're pretty straightforward. They've improved a lot of things. They had a lot of technical information on their eBay ad. So I'm like, you know what? I think it's worth a shot. Am I disappointed? Yes. Am I surprised? No. So the very first thing I saw when this thing was shipped to me was the weight. The weight of this thing was only 21 kg. There's no way that size inverter could power 15,000 watts continuously. Now, I suspect this is another peak surge rating that they have labeled on it to kind of make it more sellable or more of a fancy sounding product, and it isn't. That is not 15,000 watts. And this video is going to be why this is not 15,000 watts. It is a very nice inverter, and I'll go over what it can do, and I'm going to test it and see exactly what it can do. But immediately, other than the weight, you can see down here the thickness of the wire, right? This wire here, that wire down in there, and that wire down in there. It's like, okay, well, what's so bad about that? I'll show you, right? So that wire, I opened it up, and I took a look. It's 4 millimeters squared. This is the cross-sectional area of that wire. So that's pretty standard wire. I have some 12 gauge wire, which is pretty close to that. Right here, right? That's rated, that wiring is for a 20 amp circuit breaker. That means this should never exceed 20 amps on a continuous rating. Really, the electrical code states that you shouldn't exceed 80% of your circuit breaker's rating. So that's 16 amps. This can do 16 amps safely, continuously, no problem. Now, I'm not talking about peak surge loads or anything like that. Like when you run a vacuum cleaner, it momentarily can pull a lot more amps than that, and that's what this inverter is all about. This has a very large toroid transformer inside it. It makes it heavier. It's not a standard cheap high frequency inverter. Those inverters, they don't have surge capability. I have one laying around here somewhere. I don't know where it went. Ah, yes, here it is. This lightweight 1500 watt is a high frequency inverter. There's no transformer inside it. It's cheap. But if you're not pulling a surge current, like if you're not running a vacuum cleaner or something like that, this will work just fine. If it's just for like computers and laptops, lamps, LED lighting, this is totally fine. This will do the job. This is for bigger stuff. Like I could run my central air off of this, because my central air conditioning, well, I'll get to that, how much power it actually needs. But this wiring, so I'm going to show you. They claim, I have it in writing, the seller has said this thing can do 69 amps continuously. And I asked, what does continuously mean? He's like, well, for a few seconds on a lamp load. I'm like, look, generally continuous means a 1 hour rating in industrial terms, like a motor or something like that. But you know, I'll just give him the benefit of the doubt. If it can do 69 amps for 10 minutes even, I will shut my mouth and I'll probably won't even post this video. I'll give him the double thumbs up and say, thanks guys, this is a great deal for a power supply inverter that can do that much power. But there's no way. You know what? The other thing that's really, really obvious are these fuses. These are 20 amp fuses, right? How do you expect 69 amps to go through a 20 amp fuse? Like, it's just ludicrous why they would expect that. It's like, yes, okay, momentarily, for a few seconds, I get that, that's fine. For a few seconds, you could probably do 69 amps for that fuse, it won't blow, it's a slow blow fuse. That's not what I'm talking about. I'm talking about continuous load. I originally thought, I know it's wishful thinking, that this 15,000 watt inverter it really could power my entire house. I have about a base load of about 3,000 watts. That's with like the furnace going every now and then, the lights, and just kind of in the computer, the TV, and things like that, right? Internet router, it all adds up. And it actually goes much lower than that. At nighttime, for example, it's like a couple hundred watts. It's nothing. But this inverter needs to be able to do those on a long-term basis, more than 10 minutes at a time. Okay? So I'm sounding a little aggravated just because I've been going back and forth with many emails with the seller, arguing with him what his own inverter is capable of. So 20 amp fuse, thin wires, and I'm going to show you. If it was 69 amps, this is the kind of wire you'd actually need, right? This is burial cable. It's meant for a hot tub. The hot tub goes on a 50 amp circuit breaker. And that's the thickness of the wire, right? Never mind the thickness of the insulation. That's not what I'm talking about. Because this burial cable is meant to go under the ground where it's really wet, the thickness of that copper, this is meant for a 50 amp circuit breaker. This is meant for a 20 amp circuit breaker. This is nowhere near 50 amps. Never mind 69 amps. Like that's just ludicrous, right? It's all right. There you go. Sideways. I don't think it matters that much. So this I couldn't even plug that in there. Like it won't even fit. There's no way it's gonna work. But you know what? Let's see if this thing blows up, or I'll burn the fuse or something. I'm gonna hook this up in my garage and I'm gonna put it on my test load. My test load is going to be power factor 1, and that's important for you to understand that an inductive load like a vacuum cleaner or a dehumidifier or an air conditioner with a compressor, those are not power factor balanced devices. They have a power factor of 0.1 or 0.5 or something like that. So that's something to keep in mind when calculating continuous loads. Same thing with startup loads. Those inductors, they surge a whole lot of current to get started. But my test load has none of that. It actually has a very gentle ramp up, and I can control the number of amps, and I'm going to show you on a couple different amp meters. And I just got to hook it up outside and you'll see what I mean. Okay, here's my test. I didn't do anything ahead of time other than set everything up. I have no idea what's going to happen. So right now everything's just turned on. The load's not turned on yet. It's pulling about 0.008 amps AC, outputting 235.4 volts AC. My DC battery pack has a 400 amp fuse, a working BMS, and the total voltage is 47.47 volts. If you're curious about this stuff, you can post about it in the comments. I'm not ready to make a video about this yet. It's still under development. But essentially it's courtesy of Jack Rickard at EVTV. By courtesy meaning the code he allowed to be published for free. I had to buy the sensor and everything, but never mind that. I'm getting a little bit off topic. So let's turn on my load and see what happens. I just have to run over there, plug it in. Okay, I'm a little nervous. Load says it should be set to 12 amps, and I'm getting 13.5 amps. Okay, so far so good. I am getting, let's just do another double check here. I'm doing, let's do this here. Oop. More than 40 amps on the DC load, 68.4 amps. Let's see if that matches my sensor. I got 60.7. I'll use the higher number. No, I'll use the lower number because I'm going to be as generous as possible. This is my sensor. That's like a $150 sensor, and this is like a $40 meter. So I'm going to trust the sensor more, and it's reporting usually with CAN bus, so there's no calibration required. It's reporting I am pulling 60 amps out of these batteries. My batteries are doing fine. 3.8 volts per cell, and I'm like in degrees Celsius, they're still pretty cold. So I'm not worrying about overheating these batteries or blowing them up or anything. So let's do some math. 60 amps. Let's see. First of all, my voltage is 93.7. That's in total. That's for 4 of them in series. I have 2 of them in parallel, so I'm gonna have to divide that by 2. 92.8 over 2 times 60.7 amps, getting 2.8 kilowatt. And this one here is still 13.59 and 236. 236, 3.2 kilowatt. All right, so I'll do the math later for the efficiency. But so far, this is as I expected because I'm being gentle. This is a 20 amp circuit breaker or fuse in here. So I'm not going to exceed that right away, of course. I'm going to get up there gently. So knowing that this is doing 13.6 volts, maybe we should do that math again just to make sure. Just do 13.6 amps times 235 volts. Okay, yeah, essentially 33.2 kilowatt. Now, I want to add as well, this application that I'm doing now is just for a test. I never intended to use this fancy low-frequency inverter, pure sine wave for this load. This is not supposed to be on an inverter anyways. This is supposed to power my house and the appliances in my house all at once. That's the expectation. Am I surprised? No. Am I disappointed? Yes. Moving on. Let's increase the amperage coming out of this and going into my test load. Let's see what it does. Will it work? Yeah, 16.5 amps. Excellent. I'll skip the efficiency calculation for now. But I will check my batteries. They're doing just fine. They've barely warmed up. The voltage has barely dropped at all. I'm pulling 85.78 amps. And each module is about 23 volts. So that's 46 volts-ish times the 77.8 amps. Yep, 3.5 or 3.6 kilowatts. And that's to be expected. Oh, actually, the voltage went up. That's interesting. There you go, 239 volts. Just for fun, just to give this thing the benefit of the doubt. It is cool in here, so you have to prorate the electronics instead of derate. So I'm going to turn on that fan. Ooh, almost 17 amps. I'm going to bring it up by 2 and then see what happens. That fuse should be getting pretty toasty pretty soon. Okay, 18.85. That voltage has gone up again. If that voltage goes over 250, I'm gonna have to stop this test for other reasons, not what I expected. That's just a safety thing. You can blow stuff up if it goes over 250. And I really don't want to blow up my test load. It was really expensive and I like it. And I'll show you at the end what I'm talking about. So we got 19 amps, and I've pulled 19 amps through 20 amp fuses before. They generally hold up, especially in cooler weather like this. So let's crank it some more. Oh, overload. That's interesting. That's because this amp meter only goes to 20 amps. So now I gotta bump it up to the 200 amp, 600 amp range. Here we go. So I'm doing nearly 21 amps. And on my DC side, I'm doing about 100 amps or so, fluctuating a little bit between 90 and 100. There we go, yeah. And let's see if anything's getting warm at all. There's a lot of cold air coming through here, so let's see what happens. I could go get my temperature sensor, or not. I don't think this is going to be very exciting or very good video. This is a very good video anyways. This video is kind of boring to watch. But that's not the point. This is a test. Something could blow up anytime. This could be exciting. If you think I've done anything unsafe, please post a comment below so I can ignore you. Because you're a safety Nazi, and I don't care much for safety Nazis. Nobody does. They're from high schools to kids. Alright. I'm bored. Let's crank it up again. Remember, the seller told me this thing can do 69 amps. Let's see if we can do it.